All right, so today we're going to finish up our unit on probabilistic modeling and probabilistic inference. And it is, of course, a very fast unit. There are whole courses on this thing. But I want to cover a few main topics here. And in particular, what I want to cover today is I do want to get through and go over in some detail the Metropolis-Hastings algorithm. It's one of kind of the workhorses of modern probabilistic methods. So it's good to see it and get some appreciation of why these things work. And kind of how these, how algorithms and of course then fancier algorithms in these domains actually do work. And then I'll shift gears a little bit and talk more from a modeling perspective about a different approach to probabilistic modeling called Bayesian modeling. And the idea here is going to be that instead of taking a maximum likelihood approach where we essentially estimate parameters, think of parameters as being fixed things we're trying to estimate, we're actually going to treat kind of all the parameters of our models as being potentially random variables themselves, and we're just going to try to sample everything. That's kind of the Bayesian idea. But I'll first get through. We'll see if we can get through it all. Hopefully we'll get through most of it. I can finish up a little bit on Monday if needed, because Monday is actually going to be kind of a joint lecture on the integration of probabilistic modeling and deep learning. So when we ended, actually before I started, are there any questions about this or sort of anything? I know the project proposals are due tonight, I think the bigger thing is to submit something so that we can give you feedback rather than find the perfect thing. Though, of course, we are happy to discuss things with you. Though I can't talk right after class, so you might have to email, and I'll try to get back to you tonight sometime. Okay, any questions? Okay, so let's, yeah. Exactly, that's what we're going for. We want it to be short so we can just read them and provide short feedback for you. Yeah. You should not describe what you're going to do. You should describe the overall idea and maybe point out that you've seen related work before, if you have seen related work before. Yeah. Yeah.
How final does the idea need to be?
So it doesn't have to be final. You can change it. Ideally, you don't change it completely. If you need to, if we say right back and say that's not a good idea, then you can change it. But if you change it, you miss one round of feedback, essentially, right? So you've then lost out on a round of feedback, and you have that much more to kind of think over again. So do try to take it, as seriously as possible. But you can change it if you need to. Okay, so when we ended last time, we were talking about sampling methods for inference. And the main idea here is that instead of trying to come up with a distribution, some compact distribution over our hidden variables, we wanted to instead just be able to draw samples from their joint distribution. So in this example here, I have a Bayesian network, a chain Bayesian network, where I'm observing the last node. And in this case, we actually could come up with a Bayesian network over the remaining 3 variables. It is possible here, though I didn't really show how to do that. You can do it. But if we don't want to go to that effort, we can just think of a different tact of just trying to draw samples from it. Because really, any question that we want to answer, or most questions that we want to answer about the distribution of these 3 variables, can also be answered if we're able to draw samples from the distribution over those 3, given whatever value we've observed for the 4th one. So that's going to be our goal here, is kind of this notion of sampling as essentially a proxy for all other inference questions we might want to answer. And what I also said was that rejection sampling here, which is kind of the obvious thing to do, doesn't really work here, right? Because if the probability of the observed value you have for x4 is very small, you're going to have to draw a lot of samples before you ever observe a single sample that has that thing. And so you probably want to do something else. And so the basic idea of what we're going to do is called Markov chain Monte Carlo. And this idea is, as I said, sort of one of the foundational ideas in probabilistic modeling at this point, or at least in probabilistic inference. And so I want to spend a little bit of time on this and talk about the algorithm here and kind of why it's significant and how it works. So the fundamental idea is that we want, and honestly, what I suspect is going to be hardest of all these things is just getting used to the notation here. So I'm going to try to be explicit about this. Maybe have a separate chalkboard where I just write my definitions and I'll refer back to them. But the basic idea is that we have some distribution, P of x. And x here could be a conditional distribution. It could be multivariate distribution. It can be really anything, but we want to draw samples from that distribution. So I'm going to actually forego for a moment any sort of notion of graphical models. I'm going to kind of ignore that and just talk about distributions in general, because that's how I'm going to present the Metropolis-Hastings algorithm. So you have some distribution P of x that we want to sample from. The way we're going to do that is we're going to construct what's called a Markov chain. Now, I don't want to actually detail too much about the properties of Markov chains here. But what these are is these are essentially a distribution. And I'll use different notations for this a little bit. But what it is going to be a distribution over sort of a sequence of samples of this entire random variable. So xt here doesn't denote like a single element of this. It denotes actually an entire, all the elements of that random variable there. But what this second distribution is going to give us, this p of xt plus 1 given xt, I'll also sometimes write this as p of x prime given x. The important thing is that this is a different distribution than this p. This is a distribution that, given some value for a previous value of x, gives us a new value of x. Okay? And that's really all it is. We're just talking about some distribution, some other distribution, unrelated to p, though of course we'll relate them in a second. It's a different distribution that when you sample xt plus 1 given xt according to this chain, so basically I have my x0 at first, then I sample x1, sampled according to p of x prime given x equals x0. This is little x0 I have. I sample, I guess I should say little x1 according to the distribution over x1 given x equals the distribution of x prime given x equals x0. And I just repeat this process. And the property that I'm going to want to have here is that if I repeat this process, the distribution of xt will go to the distribution of p of x. I should go right like this. So I have some procedure where I'm going to constantly sort of resample some random variable according to some distribution p here. And if I keep repeating this process, p and then p depends on the last value too. I'll soon sort of give some examples of this that hopefully clarify it a little bit. But if I repeat this process, I'll eventually be drawing samples from my target distribution. Yeah.
So this x prime, p of x prime given x remains constant across all.
Yes. So this distribution will not change over the course of my sampling procedure. I'm going to make a slight deviation where it actually can cycle amongst a bunch of different choices, but for the most part, for now, think of it as being unchanging over the time. So we just have some distribution that gives me a sample of my next assignment of variables given my current assignment, and I just repeat that with the same sampling distribution again and again. Yeah.
You're saying that p is different than the distribution p.
Yes. So these are completely different distributions here. I mean, they're not different, but just I'm using p for both of them. Remember, the way we talked about random variables, that we talked about sort of distribution of random variable was kind of just the probability of this random variable given some other things here. And so p, for example, in our notation of graphical models, p of x1 and p of x2 are just different distributions, right? They're different things. Here, these are two different distributions. And that actually is, keeping this all in your head, actually, I will say, is the most complicated part of understanding Metropolis-Hastings. But if you can kind of keep that all in your head, it really is a pretty simple algorithm. Yeah. So those are two different distributions there. Okay, so this is our goal. We want to find we want to sample from this. And to do that, we're going to construct some sampling distribution, which I'll occasionally call a Markov chain. So this is called a Markov chain because you basically, it defines a distribution over one variable given the previous variable, but independent of all sort of things that came before it. But again, I'm not going to worry too much about the notation. I'm just thinking of this as some distribution here that I'm going to construct such that if I repeatedly sample according to this process, I will have, as t goes to infinity, I will have my samples converge to the distribution that I'm after. Yeah.
So you have some samples xt, and for each sample you're going to sample some more points from that?
Right. So the idea here is I have a sample xt. I have a single sample xt, right? This is a little xt. And I'm now going to sample And this is going to lead to xt plus 1, this is little xt plus 1, being sampled according to this distribution, p of x prime, given x equal to xt. Okay, so basically this is a distribution that tells me a distribution over next assignments given my current assignment. I'm going to plug in my current assignment as sort of the previous one and get a new assignment. And what I'm claiming is, I mean, what I'm going to have in the end is just a sample, right? I'm just going to have a sample xt in the end. It's always just a single, assignment to the random variable. But what I'm claiming is, as t gets bigger and bigger, that will approach being a sample from the true distribution that we care about. Yeah.
Are you saying that that will approach being a sample from the distribution we care about when we're drawing it after having drawn the first t, or it will have looked that way from the perspective of before we started?
I'm saying that only after t iterations, where t is a very, very big number, xt, the really big t, will be a sample from this distribution. You can only think of it really technically as one sample after the entire process, right? Even though they all could kind of be thought of as samples, that gets a little dangerous then. I mean, people do that in practice as a lot of samples from xt, and people do that. But formally, what we're really saying here is that the last t is a single sample from the distribution you care about. Okay, so here's what we're going to do. Here's how we do this. And this, again, is the Metropolis-Hastings algorithm, and it really is kind of one of the workhorses of modern statistical inference. Even though, of course, there are modifications to it now that work quite a bit better in practice, they really are special cases of this thing. And also, I should add, I'll mention this when I talk about it, but there's two versions. There's called the Metropolis algorithm, the Metropolis-Hastings algorithm, and no one ever uses the Hastings part of it, ironically. So he got his name attached to this very, very fortunately, even though no one ever uses that part. Okay. That's a little aside, but I'll say what I mean by that in a second. All right, so I think I actually don't even want, this line probably here is already going to be confusing. So let's just leave those 4 lines up there. All right, so here's how the algorithm proceeds. The key idea is, well, first we start, so here's going to be the Metropolis-Hastings. So first we start with some x0. And I actually don't care how I'm going to sample from x0. It can be random something. I mean, technically it has to have some properties, like you can transition from it to other states that you care about, but I'm just going to say it's random initialized to however you want it to be. It doesn't really affect if you do things right, it doesn't really affect your final probability at all. All right, and now I'm going to repeat the following. For t, just going on forever, because this property really only happens in the limit, though for all practical purposes it's happened effectively, after some number of times. We won't, by the way, talk about how quickly it gets there, which is a huge practical issue. This can take very long to what's called mix the distribution, and so it could actually be a very long time it takes, and I won't talk about that, but for those that are curious, I can give some brief discussion on that. So raise your hand if you are curious, maybe after we've gone through the proof. All right, so here's what we're going to do. The first thing we're going to do is we're going to sample what I'll call x tilde t plus 1. That's what I'm going to call sort of my proposed sample. So I'm going to sample a proposed sample according to some other distribution that I'm going to call q. So now we have a third thing here. We have a distribution q of xt plus 1 given xt, or I'll in fact just write it as q, usually as q of x prime given x. Right. So I'm going to sample, and this is also a distribution over next samples given a current sample, but it's a different one. And the idea here is that this distribution should be something that's pretty easy to sample from. So maybe this doesn't depend at all on x prime. That actually is, or x. That's actually a perfectly reasonable thing. It could just be random, one half one, one half the other. For continuous cases, it could be you take the value. A very common one when x is continuous valued is you take the current value of x and you add a small random normal variable to it, and that becomes your distribution q. But the idea is this is something that's very easy to sample from. We can easily draw samples from the distribution q. You had a question?
Yeah. So, okay, are we defining big X to the t, big XT, or
So what we're doing,
that in the definition?
sorry, when I write it like this, all I'm saying is that this is distribution over some variable given some other variable. So I'll use this terms exchangeably with x primes and x's. What really matters is sort of the when you plug this in with a small x or a small xt plus 1. That is telling you the actual probability or the actual sampling distribution of what that next thing is given an assigned value of the previous one. Yeah.
So Q is an arbitrary distribution.
Q is arbitrary distribution, that's true. The requirement is that you can sample from it easily, so that given whatever it is, I want to be able to easily draw a sample x tilde t plus 1.
So we can choose whichever
It has to have, well, there are some things, like if you want this to converge, it has to have positive support, or actually it doesn't have to have positive support. It has to have positive support eventually if you keep applying it. It has to basically make all points have some probability. But that's actually, I'll talk about that a bit later. Yeah.
So x0 is just some random sample generated from x, and then Q is basically.
What do you mean by generated from? I actually don't know what you mean by generated from
So you
x.
just pick, like, you have your target x, right? You want to find the distribution. You want to sample.
You want to sample from this thing, yeah.
Right. So we just want. So x0 is what is x0 is just some.
Completely random. It could be all zeros, all one. I mean, just pick something randomly.
It's the same like domain space.
Yes, it's the same size as x, yeah, because we're gonna then modify it to become a draw from this thing. But it's just pick it randomly. Set it to 0. I don't really care.
So then Q is just some distribution parameterized by, we're saying we have this history.
So I actually don't want to use the word parameterized here because that has a little bit of implications in terms of like these, kind of like the machine learning models we talked about that are parameterized things. So I'm not going to use that terminology. But yes, it's just some distribution such that given the current value of x, you can draw a subsequent value. And that does not depend on the previous history of x at all. It just depends on the current value of x. Yeah. How do we know about this thing? I haven't defined this at all yet. Yeah. I'm just saying we have a Q. I'll get to that in a second. So P is going to be sort of the probability that results from this entire sequence of steps here. But it will involve Q as well as this next step as well. Okay. Good? All right. So that's step 1. We draw from Q of x prime. In fact, I probably should just actually ignore these terms. I should just refer to, in the general case, P and Q as being x prime given x. But I might write that sometimes sort of accidentally. Okay, so we're going to sample from the distribution Q over the next state, given the current state being equal to xt. And then we do this little trick here. What we're going to do is I'm going to set my next axis. So this is sort of my proposed next sample. But I'm not necessarily actually going to set my actual xt plus 1 to be equal to that. What I'm going to do instead is I'm going to set it to be equal to, this thing, x tilde t plus 1, with some probability. So with the probability given by the following. The minimum of 1 and some crazy term here, which I'll see if I can actually get it right by this, but I believe it is p of x tilde t plus 1, q x tilde t plus, no, q xt given x tilde t plus 1. Don't worry about what I'm writing here. You can read it on the thing. Did I get that right? I got the order right? Okay, good. P xt q x tilde t plus 1 given xt. Okay, now there's a note I want to make here, which I should make on the next slide, but about these p's, because before I said that p is hard to sample from, yet I'm actually using it right there. So what's going on, right? It seems like I'm kind of cheating here, where I can't compute the probability yet I'm using it. So what's going on? So I'll talk about that in a second. But I just want to clarify the actual semantics of the algorithm first, or the mechanics of it. So and what I mean with probability of that, I mean I sample a random variable. If it, a uniform 0, 1 random variable, if it's less than this quantity, I assign it to be that. If it's greater than it, I assign it to be just the previous value xt. Right? And this is the metropolis tasting algorithm. You repeat this process, and you eventually get a random sample generated from the distribution you care about. So of course, the key part is, what's going on here? What on earth is happening in this expression here? Why does it generate a sample from the distribution we care about in the end? Before that, though, I want to mention one thing. So first of all, we often choose Q of x prime given x to be something, as I said, sort of simple, where we can generate samples from it. So for example, a very common example in when x is continuous valued is that you set x prime to be equal to a normal distribution with mean x and some covariance I. So basically what you do is you just set, in this one thing here, you basically set x tilde t plus 1 to be equal to xt plus some epsilon, where epsilon is sampled from normal distribution with mean 0 and some, maybe even small identity. I shouldn't use epsilon twice there. Some small identity covariance. Okay, so we know, or at least you can type into Python how to sample a normal random variable, and so we can do something like that pretty easily, right? We can generate samples like this pretty quickly. The second point I want to make, which is actually also very important, is about this term here. So it's about this term here, because this term, honestly, if you what I said about inference is that inference is the task of sort of assigning a probability or giving the probability of a certain assignment, right? So if our chain is like this, then this p, again, our unknown variable here is just x1, x2, x3, so the p here is really over those three variables. And so our probabilities there are in fact the solution to the inference problem. So it seems a little bit odd that we're talking about then using them in an expression, because that seems like we have to then, what are we doing here? And so what's going on here is that it's sort of actually a very important point, but it's also a subtle one. It is that even if it's hard to compute the absolute probability of a certain assignment, it's often relatively easy to compute the ratio of two probabilities when they're drawn from the same distribution that they are in our case here. All right. Now, here's why that's the case. So we don't really know what this distribution over P1, X2, X3 given X4 equals something is, right? Because, and I should change slides here. This is no longer an important statement. So if I have, X4 equals 1, say, then I know that my probability of X1, X2, X3 given X4 equals 1. Right. I can actually sort of expand these terms out according to the normal rule. So this is going to be the probability of x1. Actually, I don't want to write like this. Never mind. I'm going to write like this, in fact. This is going to be equal to the probability that x4 equals 1 given x1, 2, 3. The probability of x1, 2, 3 over the probability that x4 equals 1, right? And now computing some of these terms might be annoying. Again, it's possible for this Bayesian network, but it's somewhat annoying here. But the point here is that I can actually use the expressions of the Bayesian network to write just the numerator here pretty easily. This is actually a common trend in a lot of probabilistic models. It's if you apply Bayes' rule to try to compute a probability, the numerator ends up being pretty easy. It's all things you can compute quite easily, whereas it's the denominator that actually ends up being kind of hard to compute, because you have to sum. This is an implicit sum over all possible values of x1, x2, and x3. Right? So the nice thing about this, though, is that when I only care about computing ratios over two probabilities like this, the denominators cancel out. So that's actually all I'm going to say about this. Again, I don't expect that to be too clear, because it's a little bit, I know I'm kind of went over that fast. But what this boils down to is the statement, which I'll sort of, you have to trust me on this if this doesn't really make sense, that There are many cases where we can compute the ratio of two probabilities. That's sort of how much bigger is one than the other, even if we actually can't compute the raw probability itself. And the reason for this actually comes exactly from Bayes' rule. It's that the hard part in this, right? Because this thing here equals the sum over x1, x2, x3 of p of x1, x2, x3, and x4 equals 1. This sum is the hard part to compute. These terms are just given by the actual probabilities, the actual sort of formula of the network. And so we can compute these easily, whereas this one's hard. And so when you compute two ratios, it ends up being actually these terms cancel, and it ends up being quite easy. Yeah? Oh, wait. So you can't do which trick? Oh, the ratios. So then they're just densities. So say they're Gaussian random variables, you would just use the Gaussian density in place of that probability there. So whenever you have a continuous random variable, you always just use densities instead of probabilities, and everything translates. Yeah.
So saying that ratio can be computed.
Yes.
So assume that you have a discrete random variable, underlying random variable discrete. So you can compute ratios for all possible combinations of.
So these aren't. The thing is, these are little x values there. So it's not about all combinations. It's about computing just the probability of that one, or density of that one assignment.
Yeah, that assignment could be anything, right? It can be any x. The x tilde t plus 1 could be anything in the domain. So
it could be, but it's only a one thing at any given sampling point. It's only one. It has a definite value at a point in the algorithm. You actually are maintaining an actual value for xt.
For the algorithm to proceed, we would say that for any x tilde t plus 1 and xt we can compute that ratio.
Yeah, we can compute it. Yes, we can compute it for any, but we only compute it for the one that we actually have.
If you can do that, then why don't you just can't we like use the sum of probabilities over all the x is equal to 1 and use that to compute the probability?
So I think you're arguing the same thing here. I think you're sort of what you're arguing is actually a similar thing to this. If you can compute all the things, you can take the sum over all variables then and just compute the probability. The problem is this sum could be exponentially large. So the sum, if you have 2 to the n, if you have n variables, that sum to actually compute the probability is 2 to the n. That's the whole reason why we can't do exact inference to begin with. And so what I'm saying is there's no problem like that when you have a setting like this. That problem does not come up because you can, even though there are 2 to the n possible assignments, you can still compute the ratio of the two numbers just very quickly, in constant time. The ratio of the two densities or two probabilities in constant time for the given setting that you have. Yeah.
Wouldn't it be easier if Q is just the uniform distribution?
If Q is just always uniform, I'll actually come back to that in a second about what might happen there. But we'll come back to that. But no, it doesn't always work in that case.
That quantity, the Q will just cancel out.
Okay, yeah, so actually maybe it's a good time to mention it. All right, so this probability here, let me talk about this probability here. So this probability involves two things. It involves the ratio of the p's, which we can compute, but it's kind of, it involves some computation. That involves our true density, but we can compute. The other term is the ratio of the two q's. And it's a little bit odd because it's saying the first one kind of the bottom one kind of makes sense. It's the probability that of our sample being generated given our previous sample. But the top one is the reverse of that. It's if we were already at our next sample, what's the probability we sort of step back to our current sample? Okay, so it's sort of a reverse, the probability of the reverse event happening. And for virtually every distribution you will actually have, these two things are the same, in fact. So for example, for this distribution, the probability of going from 0 to 1 is the same as going back from 1 to 0, and those two terms cancel. And that, in fact, is the Metropolis algorithm. The Hastings algorithm is when you add those two q's there. The Metropolis one is when it isn't there. So the Metropolis one assumes what we're called reversible proposal distributions. And if you have that, you can actually drop those two terms entirely, and you don't have to compute them at all. And by the way, everyone uses reversible proposal distributions. So Hastings got his name on a great algorithm that no one actually ever uses, but everyone just still calls it Metropolis Hastings. Yeah.
Why are we interested in
in the reverse procedure? Like maybe our true probability is not symmetric.
Oh, that definitely. Well, the true probability is just probably over. I mean, there's no notion of jumping around, right? It's just a distribution. So regardless if it's symmetric or not, like over some axis, doesn't really matter.
True distribution, then from that we can create the distribution p x prime given x.
Okay.
And that p x prime given x will not be symmetric.
The p of x prime given x won't be symmetric. I agree, but I'm saying that the q still often is. And the reason why by the way, that it's not symmetric is that this thing here is I mean, this term is different if you have xt plus 1 over pxt versus the reverse, which is what the symmetric version would be. So this procedure is definitely not symmetric, but the q's still are symmetric. The proposal distribution is still symmetric. I think this might actually be clarified a little bit in the proof of this thing. So maybe we'll get to that first. I'll probably go through that fast because the main point is to understand the algorithm, which is why it's great there are all these questions. But the proof is a little bit just sort of going through some mechanics. Yeah.
So the point is to choose a Q that is symmetric like that.
Yeah, so typically people choose them because it makes the math easier. You don't have to have that extra term to compute the two ratio of the two densities. And so it typically is much easier. You can use a broader set of Qs. You don't have to worry about their density then or do some weird inference over them to know their exact density. You can just sort of sample from them. Yeah.
Can you explain the intuition of that term?
I think the intuition will come through, so I get the intuition of that, I have to admit, through the proof. That's how I get the intuition for that. So if you still don't understand it after the proof, then let's talk again about the intuition for that term. Because yeah, it doesn't really make, I mean, it's reversed, like one time has xt plus 1 on the top, the other one's in the bottom. It's all very strange. So what's going on there? Okay, so let's talk about why this works. And I'll leave this slide up here so people can kind of remember the algorithm as we go through this proof, which I'll try to go through fast. So one thing that I'm going to do a lot in this proof is I'm going to write things like this. I'm going to write things like p xt plus 1 given xt. What I mean whenever I do that, remember, is this is equivalent to saying the probability that x prime equals xt plus 1, little xt plus 1, given x equals xt. So just remember that I'm going to make that abbreviation a lot. So when I talk about little xt's, I'm talking about a single value where those are the assignments to these random variables here. Yeah?
Sorry for asking another question.
It's okay.
But when you have like you run the algorithm for while n t is large,
Yeah.
how do you actually conclude what the distribution p of x is?
Oh, you don't know the distribution of it. You just can draw a sample from it. That's the idea of this random sampling procedure, is that our goal is not to actually compute the distribution, though there are things you can do in similar ways that give you something like that. But our goal here is not to compute the distribution. It's just to get a sample from the distribution.
So, and the sample will be the last x.
Yeah.
T or
Yeah. After a certain number of steps, you just stop, where I'm not going to talk at all about how long it takes before you stop. Could be very, very long time, but doesn't have to be if you're lucky. So yeah, exactly. All right, so the theorem here, and it's a little bit of a lengthy proof, and I'm actually going to even leave out the most interesting part of it, because it does deal with some properties of Markov chains that I don't know how to easily prove without talking about like eigenvalue properties. So I'm going to leave that part out, but I'll tell you what it is, kind of informally. But the proof kind of goes in two parts. So the first part, what we're going to show is we're going to basically think about the p of x prime given xt that's defined by this whole procedure here. All right, so q is our sample distribution, but the p, the little p of x prime, q of x prime given x is the sampling distribution, but the p of x prime given x is the sort of the result of both those two steps, the sampling and then also the acceptance or rejection. So what we want to show is that this procedure will converge to give us samples from the true distribution. Okay? And so the first part says kind of a general statement about when you are given a p. So this is the number one. It's called something called the detailed balance equation. So number of step one is going to be called the detailed balance equation. And this is a general statement about a sufficient condition on p of x prime given xt. So a condition on this distribution such that when you iterate it, it will actually go p of xt will go to p of x. Where what I mean here is that p of xt is iteratively sampled according to this thing. All right, so this is going to be a generic condition on any p of x prime given x, such that if I iterate samples from that distribution, I will in fact get samples from this distribution here. It's actually not a necessary condition, it's a sufficient condition, not necessary. But what it is it's called the detailed balance equation. And the equation of interest is that p of x, I'm going to make sure I get the direction right, p of x, and now I'm writing it, this is big X, so this means for all values of x, and all values of x prime, this holds. But p of x times p of x prime given x is equal to p of x prime, p of x given x prime. All right, so like what that really means is sort of a little bit cryptic there. And I'm also going to add some other conditions, like the fact that this actually is not necessary. You can define it in more specific terms than this. But one condition, this is one of the two conditions you need to prove the thing. The other one is that your chain has to essentially converge to something. And that's guaranteed by a lot of things, but one easy property is that just the densities are all positive. So like if you have a Gaussian distribution, they're really small, but they actually are all positive. Everybody, you have a chance of selecting any sample in theory. And so again, it's going to be a really real small chance of it, but it is all positive. So in theory, you will actually converge, and so that's sufficient for convergence there. But I really want to highlight this one here, because this is going to be the main criteria of how I define this distribution such that we do in fact converge to our target distribution here. Okay. So essentially the first part of the proof is going to, the first part of the proof is going to show that this is the case, that when you have this, you have this. The second part of the proof is going to be to prove that the Metropolis Hastings updates satisfy the detailed balance equations. So, first part is it's a general property that holds, and the second part is, these updates also satisfy their properties. Therefore, when you iterate these updates, you get the samples from the distribution. So those are the two parts of the proof. The first part that I'm going to say here is actually not a complete proof. I'm just showing that, what I'm going to show actually is something very trivial, but hopefully gives you maybe some intuition about where this thing came from, hopefully. What I'm going to show is that if you are already at this final distribution here, and I apply this update, so I'm already have samples from p of x, and I sample another thing according to p of x prime given x, that I actually stay at the distribution. Like my stationary distribution does not change if I draw another sample according to that distribution. That's going to be my first claim. And then I'm going to wave my hands a little bit and say, for types of Markov chains, this means that you actually will also, as you iterate the process, you will actually also converge that distribution. Okay, so let's do the first one first. Hopefully the overall outline is okay. Actually, you know what? Maybe I'll just erase this, because it's really a one-line proof, so it's not even anything to worry about here. We know that, but the next one's the much more algebraic one. Okay, so what's the idea here? Well, the idea is actually really simple. The idea is if I have some, I'm writing it here in terms of xt plus 1 and xt, but basically I can write it in terms of a little x prime and a little x2. So the idea here is that if and let's see which one I have to sum over. Yeah, so if I sum so if I sum both sides over x, say, take the sum over x of both sides, p of x, p x prime given x. This is equal to the sum over x of this thing too, but it doesn't depend on x prime, so we can sum over that one, plus the sum over x p of x given x prime. But this term here is just equal to p of x prime, because this term, I'm just summing over x here. So for any value of x prime, this term is going to be equal to 1. And so this just equals p of x prime. All right, and this is actually all that there is to that part of the proof. What this is saying is, if I start with a distribution px and I apply this update, I wind up with the same distribution p over x prime. So what this means, again, all this means is that if I have a sample from my target distribution and I apply any update p that satisfies these detailed balance equations, I'm going to wind up with a sample from the same distribution. Right, that's all it's saying there. And so what's nice about that is that, again, with a little bit of hand waving, and I don't really know how to prove this other than through an eigenvalue properties or basically some analysis of the matrix behind this transition probability. Which I don't want to get into, but I will tell you that it's a property of these transitionary distributions that if you have a distribution that satisfies this, plus some other very minor criteria like the distribution positive, or that even it converges to have, you can reach any state from any other state, then actually no matter what your target distribution is, you will actually reach this distribution and then you will never leave it. So that's actually the first part of the proof. That says that if we can satisfy these equations here, called detailed balance, we will in fact find get samples that come from our target distribution. Yeah?
Can you explain again? So I understand the summing of part.
Mm-hmm.
From there, can you explain why this becomes a stationary distribution?
So that's just sort of the definition there, right? So if I'm in if I'm in state xt, and that's from a distribution, then the state that I get, the distribution I have over my next state, is just equal to the sum over all xt of p of xt times p of xt plus 1 given xt. That in general could be anything for any p of xt plus 1 given xt, but we've shown that it's also equal to p of xt plus 1. I mean, again, two different p's there. These are important. These are two different p's. One is the transition probability. One is the distribution we're after. And so all I'm showing here is that if I do that, this side is just my distribution for my next state, and I've shown that it actually ends up being the thing that we're after anyway. How much time do I have? All right. Okay, so that's part 1. Let's talk about part 2 now. So the remainder of the proof is just going to be about showing that the Metropolis-Hastings updates actually satisfy the detailed balance equation. And that's actually where I get the intuition about why you choose that weird term. So let's talk about this now. Okay. So first of all, I'm only going to consider the case where you actually perform the updates there, where you perform, you accept the sample. Because if you don't accept the sample, actually detailed balance is satisfied trivially, right? If x is equal to xt plus 1, then of course that thing holds for all values of x, right? So we have it trivially if we don't accept the sample. But what matters is that if we accept the sample. Right? You actually can show that the same that expression will also give you this thing if you don't accept the sample. But what matters here for the sort of the math is if we don't accept the sample. Sorry, if we do accept the sample. Okay, so the important thing here is that if in the case that we accept our sample, then what we're really doing is that we're saying that the probability of xt plus 1 given xt is going to be equal to the probability of, q, our sampling distribution, q of xt plus 1 given xt, times this acceptance probability, right? That's the, in the case that we accept it, that's the definition of our transition probability matrix. So over min 1, I don't want to write everything here, so I'll just start xt plus 1. And noticing here I'm replacing the x tilde because we assumed I did accept the distribution, the sample. So I'm actually replacing that with the actual xt plus 1. So xt plus 1 over p xt dot dot dot. Okay. So that's our distribution of our next sample. So what I'm going to do is I'm going to consider two cases. And these two cases are actually going to consider the numerator and denominator of this weird expression that we have here. And I'm consider the case first. Actually, I'm only going to consider one case because the other one's the same thing. I'm going to consider the case where the numerator is bigger than the denominator in this term here, which is called the acceptance probability. Right. So I'm going to assume that and I won't write it down because this sort of gets a little bit long expressions here, but hopefully it's actually quite simple, the math. I'm going to assume that this term, which is the denominator of that expression, is less than or equal to the numerator in that expression. And in that case, so I'm going to, I probably should write it down, but so the numerator is greater than or equal to the denominator. In this case, we have just sort of trivially that two things hold. Well, first of all, this thing, the min of 1, that is going to be, this is the same thing as there. Well, I'll just call this the numerator over the denominator. This equals 1. Right, because our numerator is bigger than the denominator, so the minimum of 1 and something bigger than 1 is 1. The other interesting thing is that if I do it the other way, so if I look at the minimum of 1 and the denominator over the numerator, I'll talk about why I want to do that in a second, and then multiply it by the denominator, by the numerator, this equals the denominator in that expression. So it doesn't seem anything that I've done that's that clever, right? Because if this is bigger, so if this one is bigger than this one, this term will be the minimum. So I then multiply this term by n, and I get my denominator out. Okay, so that seems really obvious what I've done so far. This is actually all there really is to showing that the equations satisfy detailed balance. So now we'll just actually do the math here. So here's how it works. All right, I'm trying to show that these updates satisfy this thing. All right, and I'll write, in fact, what they are. I'll hide this because I'm about to basically, it's up there, and I'm going to write what it is in a second. All right, so what I'm doing right now on the left-hand side is I'm writing one half of the detailed balance equation. So I'm writing this half, the p of xt, p of xt plus 1, given xt. Okay. This thing is going to be, well, we know that if we accept a thing, then we just plug in this definition here. So this thing is equal to p of xt times q xt plus 1 given xt. and then times the minimum of 1 in this thing here. And this, by the way, is the numerator over the denominator in our expression. So we know now that this thing is just 1. So this just equals this. Right? So we know that the last expression is 1, so we do that. And now we kind of do the tricky thing here. Now we actually say, okay, I'm going to plug in this expression here. This is the denominator in my equation. So I'm going to replace that whole thing with the minimum of this guy, 1, and the denominator. So this guy here equals just my denominator. So I'm going to actually replace this. I'm going to use the expression going this way. So I'm going to replace this with this thing. So this is 1 over the denominator over the numerator times the numerator, which is, let's just write it out a little bit, which is equal to, I'll write it like this, but then I'll write the numerator here is equal to p x t plus 1 q x t given x t plus 1. And then now if you squint, you'll see that these two terms are actually exactly just the probability of xt given xt minus 1, xt plus 1. And this is the probability of xt plus 1. Which is actually exactly what we want to show. That's the detailed balance equation there. Okay, now, the big picture here. What's actually going on here is that this precise term is chosen such that these terms cancel. And so the nature of this term, the reason why we choose it this way, is that we are choosing it such that we are kind of modifying our Q distribution in a particular way such that when we accept or reject based upon that probability, we get an effective P distribution that satisfies detailed balance. And that's actually the only thing it could be. I mean, that's the only. I mean, actually, I guess there are others too that satisfy this, but this is sort of the simplest one you can think of that will in fact satisfy the detailed balance equation, and so will actually lead to samples from the distribution of interest. And so that's the proof. All right, so let's do it. Let's take a little fun break and do a quick poll here about who understood that proof. That's going to be the poll. The whole thing. I mean, the slides are meant to be a reference for this. So there are lots of other references, but I think this is a pretty straightforward way of going through it. So hopefully, if that wasn't clear, you can look through everything again, see exactly what I'm doing there. And it seems a little bit magical, because I sort of defined the algorithm first and then derived it. Really, it kind of went the other way. It was sort of, which term here would cause it to satisfy detailed balance? Well, of course, it's going to be this one. And so you could kind of derive it that way too. But I tended to do it this way because even if you didn't really follow the proof, the crux of the algorithm itself is actually quite simple. Just gives you a way to sample from one algorithm, from one distribution, given the ability to sample from a different one. So let's talk about just some simple examples here. I'm going to give three cases of sort of really simple univariate continuous random variables that I want to sample from. And I'm going to talk about a proposal distribution and the true distribution. So in the first case, the true distribution, for example, is just the normal mean 0, variance 1. Distribution, and my proposal of Q of x prime is equal to the uniform between 0 and 1. Right? And yeah, that's sort of the. It doesn't actually depend on x. It just depends on x. It just gives a uniform 0, 1 sample no matter what. The second one is the reverse of that. It's my true distribution is the uniform 0, 1, and my sampling distribution is normal with mean 0 and covariance 1. And my third one's a little different from that. It's actually the target is normal 0, 1, and the Q there is takes the previous value of x and adds a uniform 0, 1 random variable to that. So the question is, which one of these, it's actually a yes or no for each of these. So which ones of these will actually, in the limit, generate samples? If you use Metropolis Hastings, which ones will generate samples according to the distribution you really care about? And actually, for the most part, don't worry about the actual form of the algorithm. On these, just think about what they are doing conceptually. If you iterate this process with these updates here, and think about whether or not they will reconstruct samples from the original distribution. Let's close it. Okay, so here are the results. Actually, okay, so let's actually go through these each of these. They're all actually kind of tricky for different reasons. The first one, who hasn't thought about the first one? My proposal is always 0, 1. I'm trying to draw from a normal distribution. Will that in fact give me samples from my target? Yeah. Right. So that's a good way of thinking about it, right? So the first one, the proposal is always going to be between 0 and 1. We know a normal has substantial support that's outside 0 and 1, and so it'll just never generate a sample from that. Let's skip to the third, actually, because the second one is actually kind of confusing. But let's look at the third one. What about the third one? So here we keep adding the 0, 1. Yeah.
The third is impossible because the normal distribution has support over the entire real line, and this can only generate numbers at least as large as the first number you start with.
Exactly, right. So the trick here is that essentially you're always generating, because 0, 1 is always positive, you're always adding a positive number to your sample, and so you're always going forward. You'll probably stop accepting them after a while. You just never accept anymore because you have very low probability when you start getting out far away. Because basically they'll add a number, and then the ratio of the probability of that next number over the previous one is going to start being very small, and so you'll start sort of moving not very, very slowly. But you will definitely never proceed negative again, so you'll never have samples from it. Okay, what about the second one? Who thinks it will? Yeah.
Yeah, I think it will, but I mean, intuitive explanation that you pick a uniform number in the segment from 0, 1, and then you add a small noise which can be like positive or negative, and then if you keep doing that a lot of times, you will still get like the uniform distribution. Because your pro sample is uniform.
Oh, I see. So, but no, I'm actually saying that you resample according to normal 0, 1 every time. This is not you're not adding here. It's not like the second one. So I should have actually probably put this one. That was kind of silly, maybe. I'm not adding another one. I'm just resampling each time from 1.
So the
Yeah.
support of P is a subset of the support of Q. So
Yeah, it is. Right. So does it work then?
for any x in Q, there's a probability that you can end up choosing any other x that can possibly arise from P.
Yep. So that's true. So think about the actual numbers here, though. Yeah. So there's a question over there.
So what happens if that Q generates something that is bigger than 1?
What happens if the Q generates something that's bigger than 1? Well, actually, what would happen? What would happen in the formula there? So what's P of xt plus 1 then? It's 0. So you don't ever accept it. So I guess the question is, and actually I won't answer this question because I think this is fun to think about. Does it actually converge, or does it actually get there or not? Because why is this not just basically taking random samples and truncating them if they're outside 0, 1? If you sample random for normal distribution randomly, you would not have uniform distribution over the real line, right? So is this doing that? And if so, why isn't the proof working here, or is it doing something different than that? And then why does the proof work if you're doing something different? Yeah.
So if you just truncate the values, the different values would still have a different probability.
Exactly, right. So I'm saying, are we doing that, or are we doing something different?
We're not doing that.
Okay.
This method would actually give you a more flattened
Why?
It's kind of nudging the distribution with every sample.
What?
So you start out with the normal. For every step you take, it's kind of like nudging it towards you.
Actually, but why is it doing that? Yeah.
Question. So if our next sample is outside there is 0, 1, then we just reject that.
Uh-huh.
But if it's inside, then just P is equal for xt and xt plus 1, so it just cancels out. And then Q cancels out as well, so we just accept the new sample.
So does Q cancel? Okay, so actually I'm gonna stop, but does Q cancel out here?
Oh, I see.
So this is not, I mean, this is actually not an obvious one. I don't think this is easy, but I'll let people think about whether this works or not. Okay. Because it kind of should work, right? Because you have full support over everything, so it should work. So, but why does it work? Because it seems like you're just truncating, like you said. So what actually makes it? Okay, so why would it work? Or maybe it doesn't. So you guys can think about that. Yeah.
So if a normal distribution is more likely to generate a particular point in the uniform distribution, it's less likely to be accepted. And so in expectation, you get every point with the same probability.
Right. That's right. So what isn't actually happening here is the Q's are not canceling here because there's no, it's not symmetric. In fact, there's no xt plus 1, so the probabilities are actually and it's the inverse of them, right? So you actually, this does work. Because it has support over the entire uniform distribution, it does actually work. And the reason why it works is that you actually are not symmetric in your distributions. This actually is a Hastings case, so Hastings, did something here, and that's why it works. So that's the answer. But it's actually kind of not obvious. The more obvious one is when you're always adding a small random normal thing. That's when it sort of seems more natural. This one seems a little, because that one is symmetric, but you're kind of moving around. This one's a little less obvious, but I think it's a fun example. So xt plus 1 and q of xt plus 1 and q of xt. Q given xt plus 1, q xt plus 1 given xt, and q xt plus 1 given x, of xt given xt plus 1, those do not cancel in this case because the probabilities there are not equal. They're different, right?
You would accept the sample if it's further away from the mean?
You tend to accept it more if it's on further to the right.
Yeah.
And on average, actually, those things exactly cancel. And so on average, you accept it with the exact same probability, and so you get a uniform distribution.
Yeah, how does that?
That works because of the Metropolis Hastings proof. That works because this is chosen exactly such that those two things cancel in expectation, and so that you're sampling in the limit from the distribution of your choice. So people got it right for the wrong reason on this one, but it does in fact work. Okay, we're running out of time, and I don't want to shortchange too much the next section, so I'll talk about it a little bit next time as well, and maybe do a little more high level description of deep generative models. Because and here I am going to go kind of at a high level here, but I do want to mention one thing that's quite important from the prospect or the perspective of graphical models now. Again, so now we're going back to graphical models. And this is actually a special case of Metropolis Hastings called Gibbs sampling. So Gibbs sampling is actually, you can actually derive it independent also of Metropolis Hastings, but it's actually a very simple idea. So with Metropolis Hastings, I wasn't talking about sort of a graphical model at all. I was just talking about some random variable you're trying to sample given samples from another one. You probably wouldn't do it for the previous cases because these are all pretty easy to sample from. But remember, sort of going back to our original problem, our problem that we had here was a graphical model. And maybe I don't want to come up with a proposal distribution over all three of them. How do I come up with that? These are discrete now. Do I do it randomly? I mean, maybe that's a pretty bad thing, and maybe that'll lead to really low accept probabilities. I have to run this thing for a very long time before I actually get samples from it. It's not clear, if it's any better, how to come up with something that's obviously better than rejection sampling. And so Gibbs sampling is kind of a very common way of applying Metropolis Hastings to graphical models. And the idea is very simple. And I'm going to use the following notation now. So we're done with the probabilistic tasting. We're not done with it. Sorry here. Not that lucky yet, but almost done with it. We're thinking about a different context of it. But I'm going to use the context of the following. I'm going to use the following notation. So I'm actually going to think about a general graphical model where I'm going to refer to Z as being the set of all variables that are not observed, the hidden variables. These are the things we're trying to sample from. And X being the things that we observe. So we say that we know that X is equal to X, and we're trying to sample from, basically trying to sample, maybe I'll say a little z sampled from the probability of Z given X equals X. That's our task here. And Gibbs sampling is actually a very straightforward algorithm. What we're going to do is that we're going to sample. I mean, remember, this could involve a lot of random variables here. This could involve, we'll say it involves Z1, Z2, all the way up to Zn. And each of these actually could be itself binary. It could be continuous random variable. It could be really anything. It's just some random variable. It can even be vector valued, but let's just think of them as being, within this big vector, each of these is a single univariate random variable. So the joint distribution of all of these things can be very complex, right? There could be a big Bayesian network that sort of has very complex dependencies here. But what Gibbs sampling is going to do is it's going to fix all of them except one. It's going to fix all the random variables except one. And it's then going to sample that one. So it's going to repeat. First pick I in 0. Well, let's start at 1 there. Well, first, actually, let me do it this way. So Gibbs sampling, first thing you do is you pick Z randomly. The second thing you do, so much like Metropolis Hastings, you first start with something random, then you start iterating. The second thing I do is I repeat the following. I'm going to pick some I at random. In practice, you often cycle over all the variables, but in theory, you actually just want to pick them randomly. And I'm going to sample Zi. It's going to be sampled according to the probability of I, given, well, first of all, given all our same evidence as before. But we're also going to actually assume that all the variables except Zi are also fixed at whatever current value they actually have. So also, Z, and the notation I'm going to use for that is this little not I, or the negation of I. So this means all the random variables in Z that are not equal to I, this is equal to their current values, Z not I. And the key part here is that this thing can be much easier to sample from than sort of the generic entire set of distributions here. So to see that, actually, and I actually didn't have that as an example, but let's go back to the chain here. So we know it's hard to sample all these, or I mean, again, I use the word hard here kind of, it isn't that hard in this case, but it's kind of annoying, we'll say, to sample all these things just given that one. But if I'm given x1, x2, and x4, then it's comparatively much easier to sample from x3. Right? If I just want to sample from x3, that's pretty easy. I just look at, what are the two possible values x3 could take? What's the probability of, the immediate of x3 given the actual value of x2? I don't have to worry about anything before then because those are all given. I can just write this. So, what's the probability of x3 here? Given x4 equals little x4, and x2 equals little x2. Well, this is just going to be equal to, essentially, it's going to involve a couple terms, but they're just going to involve, there's no notion of anything that happens before in the network, so I just have to compute sort of the probabilities here using Bayes' rule, just for my possible assignments of x3. Right, so that's how I compute. So it's much easier. If I had a great big chain, I wouldn't have to worry about anything that came before x2. I would just worry about x2 and x4, and I'd be done. So the upshot of this is that it's often much easier to sample from over a single variable when everything else is fixed. Now this does still, though, require some structure to the graphical model. So if the graphical model is fully connected, right, it's dense, then you don't have any real benefit. I mean, it's a little better than I guess it's a little bit better than if you had to sample from everything, because you don't have to quite do the same exponential sums, but it doesn't really help you because you sort of have to constantly use all the settings of all the other variables too. Actually, I take that back. It can still be helpful sometimes, depending on sort of the distributions you have of interest here. But the basic idea is because there's only a small number of possible settings for this, you can actually often compute this very easily, and especially so when the structure of the graphical model actually makes it easy to ignore most other variables in the domain. Right? Yeah, I mean, sometimes it's easy if you have them all, but it's fully connected, it tends not to be that easy. Okay, so that's nice because now we can sample each of these. And my claim is that this, in the limit, will give you samples over the distribution that you want, which is the P of Z given x equals x. And the way you show that is you basically just show that this is an instance of Metropolis Hastings. So here's what I'm going to do. I'm going to define my sort of Q function. I'm going to call it Qi because I'm actually going to have a separate Q function here for each possible value or each possible random variable that I'm going to sample. And in fact, what I really do is I actually pick one of these Qi's randomly, and I actually sort of average over all possible choices for Qi. So it's a little bit more, it's sort of like Metropolis Hastings with n different possibilities for the Q distribution, but that all works still. I won't really talk about too much about why that works, but it does work. But assuming for one update, I define this thing here, and that is my Q distribution. But you'll notice that in Gibbs sampling, I didn't talk about like any acceptance probability or anything like that. I didn't talk about kind of a ratio. I didn't flip some random coin and say, is it bigger or less than this some probability here? If so, accept, otherwise reject. And so all that this really involves is the reason why this holds is that it actually is the case that with Gibbs sampling, the accept probability of these updates is always 1. So with this choice of Q, the accept probability for Metropolis Hastings is always equal to 1. This is actually very easy to show. This is the proof right there. I won't go into it too much. All you basically do is you just sort of write these things in terms of their definition in the graphical model itself. So here, and again, I sort of apologize for the notation here. Here, P of x I given, like P of zi prime given zi prime naught is actually equal to the probability in the graphical model, not the Gibbs probability here. So again, I didn't want to go through this because it's a little bit annoying here, the probabilities. But essentially what you do is you write out the probabilities of these Q updates in terms of the graphical model probabilities. That gives you this next term here. And what simplifies here is the fact that you don't update any variable other than the I variable means you can actually replace some of these terms with other terms, and then everything cancels, and you just get a 1 for that whole thing. So this is the formula for the accept probability in the Metropolis Hastings algorithm. And all that I'm saying here, and again, this I actually don't want to dwell on because it's just, once you get the point here, I don't want you to get the precise math because it's just, again, the notation is kind of annoying. The point is that the accept probability with that update is always going to be 1. So we don't have to worry about kind of computing some ratio of probabilities and seeing if it passes or not. We just always do these Gibbs updates, and that gives us, in fact, a sample eventually from the distribution we care about.
And the Zi not are fixed across the iterations of time?
The zi's are the individual elements of this random variable. Everything but the zi is fixed. So you only update zi. Everything else you don't worry about.
But then that's sort of fixing your domain for Zi, right? Because once your Zi not fixed, you can only get Zi if it's that case of the.
I'm not sure what you mean by zi not. What's?
So like in the.
Yeah. So every time you pick a new I at random and you sample that I given all the rest. Yeah. You repeat the picking I at random part. Yeah. So I pick variable 2. I sample it, give it everything else. Then I pick variable 1 randomly at sample 8, give everything else, and I repeat this process, and that will converge to samples from the target distribution.
But given everything else, the assignment, ZI not, that how you assign those? Or that also you pick randomly?
No, the ZI knots are the fixed value. So again, you have a fixed value for everything. You have an actual concrete value for everything because we're generating samples. And you look at the actual value everything else has. You sample from your picked random variable. You then pick another random variable, sample it, given everything else being fixed, etc. You kind of repeat that process. And all I'm saying here is that eventually, this will in fact converge to samples from the target distribution. Okay, so next time we'll talk a little bit about Bayesian modeling, but I'll do a combination of Bayesian modeling and deep generative models. All right, see everyone soon.